purpose of my talk today is to encourage you to use SysML modeling as a framework to support software very loads and effects analysis. And I think it kind of dovetails kind of nice with some of the other talks that Anlay talked about, and also Chris Landauer, although Chris Landauer is probably pretty hard. So we can go to the next chart too. I'm going to motivate why we might want to do this because I briefly discussed some of the work that others have done and some of their lessons learned, and then I'm going to pitch 3 areas that I think SysML modeling can help in practicing the software FMEA during the development cycle. Finally, I'm going to mention some areas where we're planning future work to leverage SysML to quantitatively assess some model design choice impacts. So you go to slide 3. Chart 3, please. Oh, thanks. Now, the motivation for this talk came from a 2012 NASA fault management workshop. It indicated that failure was effects analysis with respect to software architecture is not well practiced. In fact, folks that tasked to do a FMEA are often not the same ones who actually develop software, and this kind of creates the skill tools mismatch. Now, failure was effects analysis has been applied primarily to hardware component failures, and there's been little sensitivity to understanding the effects of software resources and the design choices that we make. We kind of tend to recognize the limitations of hardware components, that they can break, but often we simplify software faults as merely bugs that we maybe should have corrected before we deploy them. But as Chris kind of hints, the software doesn't wear out, but it can actually be misused. So software for me is really about the design choices we make in addressing the use of software in off-nominal conditions. And to kind of dovetail with the previous talk, if TCP went into safe mode by crashing a router every time the message queue overflowed, we would not cause anybody. Our routers would be safe, but nothing would get done. TCP protocol we take for granted today have been designed and refined over many years to handle messaging through traffic, flow controls, flow start algorithms, varying packet sizes, sequence numbering, size windows, and a whole host of other protocol techniques. And we build this software robustness by thinking about the design choices we make and when they're appropriate. And so some of the prior research kind of suggests that SysML and UML can help characterize some of these choices. And so let's look at some of my prior work and slide 4. This fellow, Liang took a classic approach to kind of modeling, applying UML to address off-nominal behaviors. He said, let's assume we know all the dysfunctional behavior and we need to address and capture it in the UML. And he used some kind of specialized stereotypes that we can then augment our model with so that we can analyze this later. Now, this actually is a really great approach, but it does require high-quality UML representation. And but we'll see later that this actually is kind of a challenge. Now, Guy O'Shea, he comes from the medical domain where safety was real important in developing these components. And so he applied his approach in developing a robot for what he calls teleecography. That's some kind of remote ultrasound. I'm not a medical person, but his approach, his UML approach, applies use cases to prevent hazards due to support task analysis that may involve human. And he uses sequence diagram messaging to uncover these potential human error conditions. And what he did was he related like 11 different models of the sequence diagram, just like messaging, to possible human errors. For example, omitting a message could mean that a human skipped a protocol step, or sending a message with wrong data could represent some human typing in a wrong value. But he claimed that by using this FMEA and UML, it was useful to focus on these critical and weak design points from a safety point of view. Okay, let's go to slide 5. David's work tries to address the skill disconnect between the UML users, the design engineers, and the dependability analysts. So instead of assuming, like Lace Cohn did, that all the dysfunctional behavior is known a priori, David wanted to automatically deduce this dysfunctional behavior from the UML. So he built on Guilloche's messaging approach, and he attempted to analyze the sequence diagram and auto-generate FMEA entries for every message sender point on the sequence diagrams. He characterized different failure types, but you might, as you might expect, he generated a heck of a lot of data that needed manual review. So his later work kind of suggested that he needed to kind of integrate some kind of component database that has some kind of meta information to be able to characterize and recognize some valuable context. Okay, let's go to slide 6. Chart 6. Okay. Well, what are the lessons learned? The prior work shows that UML is appropriate for the dependability modeling analysis, but there's been kind of a large focus on functional behavior. Namely, is that behavior there, or isn't it there to providing the service, or isn't it at the component level versus addressing like non-functional areas like performance. This is a simplified view that can overlook degradable service options driven by non-functional behavior. I want to make it a side point is that one of the interesting comments that came out of NASA's workshop in 2012 was a fellow who really wasn't a fault management expert, but more of a semanticist. And he said the way to view a fault is a goal that hasn't been achieved. And when you think of it that way, you enable yourself to start thinking about degradable systems as opposed to a service being present or being just up or down. Okay, and that's an interesting thing to keep in mind. Anyway, automated FMEA really without some kind of context generated lots of data. Dictionary was used to kind of characterize some of these contexts, but there's some work on addressing design choices that's still needed. Let's go to slide 7. Well, we don't always have high-quality UML models in practice. That's the challenge. Like in an agile-based development environment, requirements and design kind of get revealed in nuggets, not all at once. So what gets represented is often incomplete, even with respect to this implementation. We found in looking at our flight a lot of flight software from different missions is that even a faithful UML representation is only captured by 40 to 60% of actually what's being built. So software FMEA focus has not been really incorporated into the requirements discovery process or even in the use case scenarios. So the challenge is to try to promote kind of a modeling-based approach that recognizes these design choices and their impacts on the behavior and permit some kind of analysis of this effective optimal option. Charlie. The approach I'm pitching to use SysML is to use SysML models as a framework to capture some evolving software FMEA issues. Okay, so applying software FMEA during the development cycle is kind of viewed as a risk mitigation effort. But in this talk, I'm going to kind of focus only on 3 areas. There's all kinds of different dimensions you can go into in terms of testing and stuff. But I'm going to look at requirements discovery during evolving design, capturing functional behavior options and the software issues in formalized use cases, and then finally using the SysML framework to conduct specification conformance during the life cycle. Now to do this, we can develop UML extensions, use the theory types, capture and annotate the information in context, and leverage these standard SysML parametric models to define these figures and errors and be evaluated using the tools outside of SysML. And that's sort of, that's kind of a normal, classic kind of way of using SysML. So it's nothing really new in terms of how we're stretching SysML. Okay, let's go to slide 9. Okay, in this cartoon, I'm trying to talk about a little bit about how requirements make discovery. For requirements discovery management, I'm looking from the perspective of a system engineer reviewing, say, some kind of architectural development of the flight software. Okay, maybe you may be invited to somebody's requirements review or design review, and you're looking at how the software is being developed, and you may have an itch about some feature that's not being captured. Okay, if the software FMEA is applied early in the design process, it's likely that new requirements will be discovered. Like in an agile-based development environment, adopted requirements and functionality of the to-be-developed subsystems will almost certainly be discovered as the design unfolds. So typically one requirement may refine and be derived from others. That's kind of like what I'm trying to show here with the new requirements. Often during the reviews, though, the design code reviews, clarifications of the intent, which could manifest themselves as either shalls or wills, are made known. The effects of these design choices can be agreed to, okay, or maybe not. These design choices can capture initially as a discovered requirement that I show in yellow. Even if there may be a reluctance to introduce new shell requirements in the name of requirement free, it can usually, you can think of these not necessarily in terms of just requirements alone, but concerns, okay? And I kind of want you to kind of think of using SysML outside the box. Don't necessarily be constrained that, oh, I have to create a requirements diagram to do this. You could use a requirements framework for capturing any kind of concerning one and stereotype all kinds of new things on it if you wish. Okay, so keep that in mind. But even if there is a reluctance to introduce the requirements against its baseline, you can capture that. For example, the baseline requirement may require that an input be checked for validity. There may not be any requirement for the case when the input is invalid. So you may, this is a design ambition, it can be filled with a discovered off-nominal requirement and later verified using SysML figures of merit that kind of show there in the back. All the green stuff there on the chart is the standard kind of conformance checks that you do using SysML parametric model. Now, in cases when there's no agreement on the solution to the discovery requirement, it provides a placeholder for later analysis. It can lead to other representation issues, such as test cases, off-nominal state conditions, stuff like that. I'm also showing, there's other associations. You can tie these to not only these test cases, but there's the earlier talk that Andre talked about. You could put in problem reports, discrepancy reports that occurred. You start mapping these so you can find out real hotspots in your software. There's think outside the box here. There's a lot of different ways you view this as a framework for later analysis and navigation because SysML, because it's integrated well with SysML, provides an ability to navigate the software architecture. So let's go to slide 10. Now, in this chart, we should really be thinking about integrating functional software behavior represented as use case scenarios with the software failure modes and their mitigation strategies. And this is usually not done. And the use cases I'm talking about aren't the bubble diagrams that you might think about, but they're more formalized in terms of delineating nominal, alternate, and exceptional execution behaviors. The advantage of a formalized use case can identify not only the problem context, such as these pre and post conditions, but can clarify its mitigation. Is when, like for example, in an agile integration build, when is that build going to be expected? So there's a lot of meta information to capture. The real challenge in taking this kind of approach is managing the level of granularity on the use step level. As Chris kind of hinted, if you really want to get into a lot of details of how anomalies occur, you need a lot of data, and I kind of agree with that. The challenge, of course, is being able to manage that complexity. Okay, let's go to chart 11. Okay, now this chart here describes some of the ideas behind formalizing use cases, how they can be exploited. You can kind of read this later. I'm not going to really get into that because I kind of want to go to the next chart to kind of give an example of some of the things that are on this chart. So let's go to chart 12. Okay, this is kind of an eye chart, sorry, but what I'm trying to show here is I'm taking I'm representing on chart 12 as a table, okay? And oops, I think I just have a problem because my machine just logged me off here on my end. Hang on a second, guys. Oops. Okay, thanks. If I don't move the cursor, sorry. Anyway, what I'm representing here in chart 12 is a table representation of a use case that contains software FMEA information. Okay, and I'm putting meta information in it. The way this would actually get represented in SysML will probably be through some informatics that would import this information. It's very easy to do that in SysML, but that's kind of out of scope with this talk. But the reason I'm putting it as a table so that we can cram a lot of information without worrying about a lot of the diagrammatics that SysML can contain. I don't build SysML models to view as a human. I view it as a framework for me to do automatic analysis and so forth. Okay. This slide in the backup charts also is a fictional satellite example, so if you kind of don't believe it, then I got it all screwed up as plain me. It's not pulled from anything, it's real. In this example, what I'm doing is I'm assuming that there's a baseline requirement called rec attitude 10. And what that is the data, it's a data in an attitude request from the ground, has to be normalized within some constraint value. Okay, this is a baseline requirement I'm showing up in white there at the top. It creates a precondition that assumes that the attitude request is not currently in progress. So during the requirements review, 2 discovered off-nominal requirements were identified. These are shown in pink. There's one requirement called rec attitude 10-1. It's supposed to handle the case when the attitude request is already in progress. Now, in this case, the postcondition for this requirement indicates that the command will be ignored. Now, and the software FMEA idea is then associated with it. If you look at it, you'll see on the side, it has an attitude F210-fail indication. So now we're creating that information within a context that captures software FMEA data. You can put all the software FMEA information into it, mitigation choices, mission effects, assumptions that you have, references to other things as well. Now what's different here, however, is that the use case context now contains this mitigation, namely that the command will need to be resent. Okay? Now this mitigation that's captured here in this context here, of course, affects the operations. Okay, so that a full resolution of this condition would require an operating contingency command to be developed to address it. This is a software item that now, through a design choice, has an operator impact. Okay, this is a vital piece of information. In particular, the resend mitigation makes another assumption that the attitude request is never part of some synchronized set of command blocks that cannot be interrupted. Like, for example, if you want to send a command sequence to do a maneuver, you may want to have a set of these attitude requests to come up, and you may want to execute these commands in a certain order. The assumption is listed as part of the software FMEA description, and if it turns out to be unacceptable, another design choice, maybe how to queue this request, could be required. Now, the need to create this discovered off-nominal requirement was driven by design choice that ignored an in-progress request. But another design choice, such as queuing the request, could alter the mitigation that affects the ground. The queuing, if you pick the queuing solution, that would create another off-nominal condition as to what are you supposed to do when the queue is full, and maybe that would spark other prototyping activities that you might need to test to figure out what would be an appropriate queue size. Now, the second off-nominal requirement, listed there as rec F210, deals with a case when the request cannot be normalized. Okay. Again, the use case provides a context for which the design choice to use validated but stale data to resolve the request. This becomes explicit. Now, the test scenarios could evaluate the soundness of this choice, to propose to determine whether or not the time instability in taking this approach is reasonable. But when the request is invalid, now a log service will be invoked to log that anomaly. And the log service itself, and we showed that at the bottom here, those last 2 requirements are presumed to be baseline requirements that recognize that the log function is a useful thing to have. The log service use case may be reused in other use case steps, okay, because it's kind of service. Now on the last line, we note that there's a design choice even that. To reboot the system should a log error occurred. Now the effect of this choice may be, will be that the mission is disrupted. And later, someone might review the log service and say that it actually is required to be fault tolerant, and then a design choice to whether lose the log data and disrupt the service will be is what's required. So hopefully what I'm trying to show here is that in this example is that integrated use case steps can help discover new requirements, provide adequate off-nominal context, make software and mitigation more explicit, design and their design assumptions for review. SysML offers this kind of framework in which diagrammatic relationships can easily be navigated, analyzed, and possibly we could use them to identify new test scenarios. Let's go to slide 13. Okay, in this final example, this slide gives an example of how SysML can act as a framework for supporting conformance and implementation to specification. The construction of the SysML conformance model is kind of straightforward, and skeleton for how to do that is shown in some backup charts I have. But the functional failure analysis specification, it's a document that explains how to detect, isolate, respond to particular hardware component failure. Okay, in the example I'm showing here, we're focusing only on whether or not the code implements an isolation logic that's specified in the FFA spec. So to check for conformance, the FFA conformance with the code, we take the spec. You can see the little stuff at the bottom of the yellow box at the bottom. As we're taking the FFA spec, we extract the FFA data from the spec, and for a particular failure identifier, we check this data. It indicates whether the failure identifier could isolate the condition being observed, and such as the criteria like persistence and so on, to verify the default condition is in fact failure. The bottom line of the chart takes the code, and it was parsed out, and the data was extracted from it for each failure identifying condition. Okay, and so this was actually possible. We were able to pull this out of the code because the flight software used a design pattern to implement isolation checks. And I strongly recommend that folks, as they develop flight software, that they do not underestimate the use of design patterns, naming conventions, and all that stuff, because that does help in the analysis of the software for conformance checking. What we did have to do, though, is we did have to create a dictionary. I didn't show this on the chart. We had to take a dictionary that relates the specification of the code data that was being developed, and we tie it to a back-end evaluation tool that made these comparisons. The results of this result data that was used to drive the figure of merit parametric models with SysML. So basically what it did was it allowed us to take data that was outside of SysML, analyze them separately, generate a data that could be fed in a parametric model, and then populate a framework within SysML that can touch a lot of things. Code, test procedures, so you can navigate why a particular failure had. You can navigate not only that some particular failure identifier failed, but what other things will relate to it. Okay, let's go to chart 14. On the last chart, as I talked about, I said that constructing a SysML conformance model is straightforward. Well, although that may be true, it doesn't mean it's easy. In fact, it's a heck of a lot of work. So what we're looking at is how to auto-generate some SysML conformance models automatically. Okay, a real astute observer in the audience will probably say, hey, but Bill, you don't have to build a SysML model to support a conformance evaluation that you did outside of SysML. Well, that's true. And the point here is that not everything needs to be in SysML. And frankly, you'll need to strike a happy balance between what analyses and what data are in and out of SysML, and what value you gain by making it available to a SysML model that you can navigate. You should recognize, though, that SysML and UML integrate well together, and that they represent software architectures from various viewpoints, and links to analysis outside the tools of SysML is possible, and it's quite common. System engineering data and software architecture representations are going to continue to evolve, and how you construct these models will enable future analysis because they inherently have a pattern structured representation, and that's one of the reasons why we're motivated to use it. We believe that by applying Prolog's pattern analysis capabilities to query over these models, we can gain a lot of deep insight across system engineering and software engineering areas. The degree that you do this, say, within SysML or outside as, say, part of the database, whatever, that's up to you, but I think you should be starting to think about how, if you want to capture architecture-type software architecture relationships, don't throw UML law representations out. With respect to the software FMEA design choices, we'd like to augment our SysML UML models to quantitatively assess design choice impacts on mission accomplishment. And we're looking at how we can try to apply reward-based models using, say, performability analysis for that. Now, to scale this, as Chris kind of pointed out, and I think a lot of other folks too, that onlay, especially if you're dealing with literally thousands of possible discrepancy reports, or as the prior research showed, in terms of how many interactions you have, scalability for generating this models efficiently will need to be really addressed. We believe that if we have this auto generation capability that we built with some smarts, we'll be able to assist flight software systems that must emphasize mission continuity through graceful degradation, all simultaneous fault management, and goal-oriented fault tolerance.